Hello everybody and welcome on this session about my 10 biggest Azure mistakes I want you to learn from. My name is Toon van Houten. I'm CTO at Noest, and with Noest we want to make people's life easier and more efficient, and we do that by crafting end-to-end solutions on the Microsoft stack with local people from the west of Flanders. Next to that, I'm the founder of Your Azure Coach, and with Your Azure Coach we organize Azure trainings to infuse people with our experience so they can confidently design, build and run Azure solutions. I've been awarded as a Microsoft MVP for the last 5 years, mostly thanks to my contributions in the Microsoft Enterprise Integration area. So this is about my 10 biggest Azure mistakes. The first one is, maybe you can guess it already, about networking. So I had a customer case where they wanted to build some internal APIs. But there were some special requirements. The API contained some sensitive data. That was some HR-related data, so sometimes private and personal data. So security was quite important over there. And the data resided in a SQL database, but not an Azure SQL database, but a SQL Server database on premises. So we had to connect to that one too. So as an architecture design, there was already, I was lucky about that, already a hub and spoke model, network model in place. So we had the hub VNet and we got our own spoke for this solution. We chosen for Azure App Service, one of the most mature services I think in Azure, and a perfect fit to deploy web applications and web APIs like we had to do this time. We used Azure AD for the security. From a networking part, I was lucky because there was already a site-to-site VPN in place. So we had already a VPN gateway in the hub, which was able to connect to the SQL database on premises. But of course, our web app we've chosen for the cheaper tier. So it's not an app service environment. It was an app service in the multi-tenant tier. So we needed to configure VNet integration so it could connect from the outbound side via the spoke into the hub network. And of course, we didn't want to have public connectivity. So what we did is we enabled a private endpoint for the web app, so it got a private IP address within our spoke network. We wanted to disable access to the internet, public access, so from the internet the API was not reachable. And then last but not least, we had an internal application that existed already that could consume our web application, web API, my apologies, via the private IP address that was offered by the private endpoint. We also configured a DNS zone, so everything was in place. But now the problems came up. Two issues. From a priority perspective, the Azure AD authentication was a little bit deprioritized. It was not an issue at that moment in time for the functionality that we had because we had already network security. But we made a mistake in our infrastructure as code, and the web app was still available on public internet. So there's a flag enabled public access that is available on app service. By default, that flag is set to true. So by default, your app service is available on public internet, and we forgot to turn it off. So of course, that's not good, and you want to avoid such things in the future. So there are actually two solutions to this problem. The first solution is more the old-fashioned solution, where we say, okay, the development teams, they don't need to provision infrastructure anymore. No, let's do it with the infrastructure team. So we can do everything ourselves and everything will be consistent. So that's good for consistency, but there's a problem for the velocity. If everything needs to go through a ticket, they need to wait in the queue until the ticket is resolved and then some modifications need to happen. You lose velocity and you lose a lot of the advantages of the cloud because the cloud can give you speed and agility. So my recommended way to solve this solution is to go and provision Azure landing zones. So the infrastructure team should be responsible to provision Azure landing zones with specific guardrails. Guardrails that limit the functionality that you can do within Azure. You could, for example, limit the number of services that they can use. And you can, for example, configure an Azure policy that prohibits the creation of app services with a public endpoint. Or you can even do a policy that automatically makes sure that every app service that gets created is only available via private endpoints and not on public internet. So this is the way to go, not like in the old way on premises that the infrastructure team is in charge of everything. No, provision landing zones and make sure with Azure Policy, with that rules engine that you can inject in your Azure environment, and you can apply it on different scopes, thanks to that rules engine, you are still in control of the security, while you give a lot of freedom to the development teams to gain speed and to build rapidly applications over there. My second problem that I faced, or mistake that I made in the cloud, is also about security. Again, let's look first at the use case, at the customer case. And it was a customer who had a strategic goal to share data seamlessly with customers and suppliers. And they wanted to do that in a self-service manner. They had already quite a few point-to-point integrations with their suppliers, and every time adapted to the possibilities and capabilities that that supplier had. But actually it was a lot of custom development, and also from a support perspective, there was quite some work to do to make sure that all these point-to-point interfaces worked. So there we decided to do it another way, and to make sure that that customer could expose its own APIs and say to the customer and suppliers, hey, here we have our APIs, and you can find the documentation online, there's a smooth onboarding, and you can just access the APIs. So that was the use case. And of course, that's one of my favorite topics. This is here where Azure API Management comes into place. So Azure API Management is typically positions between your API consumers and your backend APIs. So the consumers could be internal application development teams. They could be residing on-premises in Azure Cloud or in any other public cloud out there. You could also have external API consumers, like with this case, this customer had other suppliers and customers that wanted to connect to those APIs. So API management is a kind of an abstraction layer that hides away all the complexity and the diversity of your underlying APIs. Because you might have more old-fashioned APIs that implement a SOAP standard. You might have newer, modern GraphQL API or RESTful interfaces. So API management is there to give an abstraction layer on top of it. One of the most important features of API management is security. It might be probably that every backend API has a different way to perform the security, but of course, towards your API consumers, you want one uniform and standardized way to do security, preferably by OAuth 2 and OpenID Connect. Routing is also important. It might be that you don't want to expose all the functionality of your backend APIs to your suppliers. Maybe you only want a subset of one API, or you want to merge functionality from two APIs into a new virtual API that you want to expose to your suppliers. So that's functionality that API management brings. Transformation is also a good feature that API management has. For example, you don't want to expose old-fashioned SOAP APIs to your suppliers. Maybe you want to pick some of those endpoints, expose them as a RESTful interface, and API management can do the transformation for you towards the old-fashioned SOAP API. So you can modernize your APIs without needing to change your backend APIs, which is very handy. You can optimize your APIs. You could add caching, for example, versioning, and all these kind of things to make sure that you have a robust API program that you can offer. And a big advantage is, of course, all the API calls go through your API management instance. So if you configure your monitoring the right way, you have very valuable insights on the usage of your APIs. Who is using your APIs? Which APIs are they using, and at what time? What is the success rate of your APIs? Are some of the APIs failing a lot? Then maybe you should investigate over there. So there's a multitude of data that you can capture over there that gives you insights and can help you make decisions also on what topics, what business areas are more important from an API perspective. And then last but not least, you need to have engagement with your audience. You don't want them to send an email and you need to send them a PDF with all the documentation of the APIs and back and forth. So API management, Azure API Management comes with a developer portal that allows you to give access to your customers or suppliers and give them a subset, access to a subset of your APIs that they are allowed to consume. And in that way, you can go really into a self-service manner. If you look a little bit deeper in how API management works, it has the concept of policies. And you have actually policies on 3 levels. The lowest level is the operation level, where you could do, for example, caching and transformations. Such a policy is just a very simple XML file with some policies that, of course, you can find in the documentation. But there's an important element, and that's the base element. And that base element is actually referring to the policy on the higher level. So the policy higher than an operation is on the API level. So if you configure some functionality like, for example, rate limiting on API level, it will be applicable for all API calls that go to that specific API. So also that policy is again an XML file which contains a base element on its own, and that base element will refer to the global policy, and that's a policy that is applicable for every single API call that is performed on your API management instance. What did I now do? I did some copy pasting of policies in my code base, and I removed the base element by accident. So you might think, oh, that's not that bad, but if you remove your base element, you remove actually the reference to your global policy. And on the global policy, we configured our security that was applicable for all the APIs. So by this mistake, I had no security anymore on this single API, which was, of course, a big security risk. So how can we avoid this? Because, of course, we are all human, we all make mistakes. You can avoid this by validating your API management policy XML files in your release pipeline. You could do that in Azure Pipelines, you could do that in GitHub Actions, or in any other tool. It's a very simple script that you can find on my blog that can help you with that verification. The third issue, again, a customer case, and it was a customer who had a buy before build strategy. So they didn't want to build everything custom. They wanted to search on the market for tools and SaaS solutions that help them run their business. And only for that 10 or 20% that they didn't find a solution for, they wanted to do custom development. That, of course, means that you have a quite heterogeneous application landscape, and that there's a need for real-time communication and integration between those applications. That's where Azure Integration Services comes into play. We have 4 services in that offering. Logic Apps, which has quite some adapters and workflow logic to run the integrations. API management to expose your API endpoints, because integrations often go through APIs. We have Service Bus, which is a queuing system in the cloud that offers publish-subscribe principles. And Event Grid is also a publish-subscribe engine, but it works more in a push-push model. So I had a design, a decoupled design, where the source was sending events. For example, a new product was created, a new product in the offering, and that needed to be sent to 2 other applications. So we had a Logic App that was subscribing on the source when that event occurred, and that Logic App exposed and published the event on Event Grids. Event Grid was configured with 2 subscribers, one for SAP and the other one for Dynamics, if I'm not mistaken. And in that way we had a decoupled design, and we could add other subscribers if needed. What was the problem now? On SAP there was a maintenance window, so we had to stop the integration for 1 hour. So what did we do? We stopped the Logic App, but then new events came in, and Event Grid started pushing these events to our Logic App. It received an exception, and it started retrying over again like Event Grid does. But of course this was quite a problem, because we had no graceful way to pause the integrations. And from an exception handling perspective, it was also not perfect. So what was the solution? Actually very simple, but instead of using Event Grid, my advice is now use Service Bus. Service Bus has quite some advantages compared to Event Grid if you are doing reliable and enterprise integrations. The first one is maybe the most important one. You can choose the processing speed yourself. So you can stop processing, the messages will always remain within the queue. If you use Event Grid will fire events towards your service. Here you can control the processing speed yourself. You can pause a little bit and continue on your own pace. Service Bus is also a lot more firewall friendly. You don't need inbound connections. With an outbound connection through the firewall, you can connect to Azure Service Bus. So from a security perspective, a lot better. And it's also more reliable, because if you use the peak lock pattern, you have actually at least once reliability. You get also more control and visibility. If you stop processing the messages, you can inspect, you can peek into the message when it is queued. This is not possible for Event Grids. And you could also have support for ordered delivery, FIFO, first in, first out. If that is needed, you could implement that by using Azure Service Bus sessions. My next mistake actually that I made is about automating everything. I think it's a no-brainer when you go into the cloud that you automate everything. For many organizations, it's already normal that you automate the release of your code, but also the infrastructure should be automated, definitely in the cloud, because one different setting might make a huge difference between two environments. So at the time that I had to make my decision for the project, I think it was 6 years ago, there were only three options: Azure CLI, Azure PowerShell, and ARM templates. I have a developer background, so the ARM templates, that was too much JSON for me. Azure PowerShell was more for the sysadmins. Azure CLI was well suited for a developer like me, so I've chosen that option. And actually it went pretty well. So the documentation is also very good on Azure CLI. So I did an AZ resource group create, a storage account create. So just with a few commands, and I had actually my infrastructure up and running. I run the script and everything worked fine. But then I run it for a second time, and then the issue became, I got exceptions. Yeah, your resource already exists. So it's not really idempotent the way Azure CLI works. If you do create, but the resource already exists, it will not do an update for you. So you need to add your own logic, if-else logic, to check, does the resource already exist? And if it does already exist, you need to do an update instead of a create. So yeah, my simple script became more and more complex, and it was not easy to manage. And actually, I had to do this exercise first. I had to look at what approaches did you have for infrastructure as code. And you have a declarative and an imperative approach. If you look at the declarative approach, you describe what you want to achieve. You describe the end result, how your environment should look like. And the system, in this case Azure, will take all the necessary steps to make sure that you get to that desired state. So it will check what properties do we have, what is the difference between what you want and what is already in Azure, and the difference will be applied on your Azure environment. So you only need to think about your desired state. You don't need to think about in what current state am I. Do I have a blank environment, or do I have already deployed something from an infrastructure perspective? This is a little bit strange because from a developer perspective, I'm more used to work with an imperative way, like I did with Azure CLI. And in an imperative way, you give the commands to the script and say, okay, first do this, then do that. So you are responsible for all the steps. So my highly recommended approach for infrastructure as code is to go the declarative way. It might seem a little bit strange in the beginning, but it's fantastic and it's a lot easier. From an infrastructure as code perspective, there are quite some options in Azure. You find them all over here. I think the most two popular ones are Bicep and Terraform. Bicep is a lot improved version of ARM templates. It's still using ARM templates underneath, but it's a domain-specific language on top of ARM templates. It has a very good extension in Visual Studio Code, so I'm truly big fan of Bicep. So my recommendation is always, if you don't have any multi-cloud requirements, just go for Bicep. If you have multi-cloud requirements, I think you should consider Terraform or maybe Pulumi. My next mistake I want you to learn from is about this use case. My customer had documents that were uploaded on the website, and they had to be processed as soon as possible. There was a need for a validation on the content of those documents. But to have a good customer experience, that process needed to go pretty fast. So actually we had two options. We could go for polling or for webhooks. If we go for polling, you have a client application, in this case a background job, that is interrogating the server on several intervals. Hey, do you have events for me? No, nothing to share. And 5 seconds later, again, do you have an event for me? Nothing to share this time. And then suddenly the event occurs, but only a few seconds later we poll the next time, and then yes, we get an event back. So you see, quite some resources are spent before actually the events get sent out, and the event is not received that fast. With webhooks, it's a little bit simpler. I compare that always with a good project manager. The project manager is not there every hour at your desk. Hey, how is it going, Toon? No, the project manager is just saying, here's my phone number if there's any problem, or you want to validate some stuff with me, here's my number and contact me. And that's what we do with webhooks. We let the server know, here is our URL or URI, and just contact us when you have an event. So when the server-side event occurs, the webhook system will send an HTTP request to your endpoints. And this is actually what Azure Event Grid is providing out of the box. So the documents that were uploaded, they were uploaded on blob storage. And Azure Event Grid has quite some native Azure events that it supports, and blob storage is one of the first that it's ever supported. Be aware that Azure Event Grid also supports partner events. So if you do, for example, integrations with SAP, Auth0, maybe Microsoft Graph, all these events are now also available in Event Grid, so you can react on these. So in this case, we had a storage account, the document was uploaded, and thanks to the Event Grid, we could fire off an Azure function that processed the document. An Azure function serverless technology was perfect fit for this use case. But to have some reliability, what did I do? I stored the documents once they were processed in a kind of an archive folder. If we needed to do some reprocessing or we needed to contact these documents for later purposes, we still had it. But the problem was, and maybe you see it already, I created an endless loop, because every time I archived a document, it triggered again my Event Grid, and my endless loop became bigger and bigger. So the solution to this problem was, putting a filter on your Event Grid so it didn't fire for every document, but only for the documents in the root folder and the root directory, and not in the subfolders. So that solved my problem. But in the meantime, until we detected the issue, quite some money was spent. So here you could avoid the problem, of course, by applying the filter, but also make sure that you configure budget alerts. It's one of the first things I do now on every new project. Check with the customer, do you have already budget alerts configured? If not, I just apply them on my scope, on the scope that I get, maybe on a resource group level, on a subscription level. You can set alerts on the actual costs, but also on the forecasted costs. So the forecasted cost is of course better, because if you have a peak in the cost, you will identify that sooner than later. I've seen also that there's now a new alert, which is reacting on peaks, sudden peaks in your consumption. So that's of course very nice for these kind of scenarios, because peaks, can lead to excessive costs. So if you can detect them early, that's very nice. So Azure has now some anomaly detection and provides you the ability to also configure alerts for that. I had some similar situations where we had some excessive costs and where budget alerts helped us figuring out what happened. One of the things was performance testing on UAT. So this is an execution plan of a SQL server, SQL database in the cloud actually. So we did some performance testing, so we increased the database to a quite expensive size, tier, and then we did some performance testing. Everything went well, it was Friday evening, we were very happy, got some pizza and then went home. But we forgot to downsize my apologies, the SQL database again. So that was a quite costly affair, but luckily it was detected pretty fast by our budget alerts. The second one was about monitoring. I always advise people to instrument the code, and that's what we did in an IoT project. We instrumented the code with application insights. But of course, IoT, quite some messages were processed per second, and we were sending the events at the debug level. So you can imagine quite some data was being ingested, and the invoice only of the application insights was quite high. So yes, instrumentation is good, but make sure that your log level is configurable and that you configure sampling, and that you only send a few percentages of the log events effectively to your Azure application insights. The sixth mistake I want you to learn from is about mission critical background jobs. So we had quite some integration and background jobs running, and it was very important to detect if they were all running fine. And the customer wanted to have a centralized view on all the integrations, on all the background jobs that were running. Because those background jobs, they are like the internet and the network. If it works, it's normal. If they are down, people are complaining, of course, because they were used that data is synchronizing between applications, and now it doesn't happen. So this customer wanted to react before the business even complains. So we did some kind of a proof of concept, and there we've seen, okay, on all these integration services like Logic Apps, but also Azure Data Factory and so on, you can configure diagnostic settings. And those diagnostic settings emits logs, default logs that are offered by the service itself, and you can send them to event hubs. Event Hubs is a real-time streaming platform, so that was perfect fit for our use case because we wanted to have real-time insights into the integrations. So we configured on every resource type the diagnostic settings to be sent to Event Hubs, my apologies. And then we had an Azure function that consumed the events from the Event Hub, did some transformation and correlation, and inserted those events into a SQL database. And on top of that, we've built an API that was serving, let's say, the dashboard that we needed. So this design worked pretty well in a proof of concept phase, and then we started to semi-productize this, but suddenly, some issues were detected. First issue, those settings were forgotten. So developers and architects, they were creating new integrations, but they forgot to turn on the diagnostic settings, so we were running blind for these interfaces. Another one is the serverless function started throttling, because the database has, of course, limits from the number of connections that it can allow. So there were quite some events coming in, so our serverless functionality was scaling, but of course our database hadn't enough throughput to handle all the loads. So we needed to increase the size of our database, and it became also too expensive. So actually what we did build a solution, but it was not scalable. And definitely the Azure function in combination with a SQL database is not recommended if you have high loads. So Houston, we had a scalability problem, but luckily we were able to solve it. And actually in a very simple way. Instead of configuring our diagnostic settings to send to Event Hubs, we did send it to Log Analytics right away. Also, with Event Hubs and Log Analytics, there's a small delay in it, so it's not because you send it to a real-time platform that it goes faster. So the ingestion time towards Log Analytics or Event Hubs was almost the same. But we didn't want the people to configure the diagnostic settings themselves, so we created, remember, an Azure policy that enforced those settings. So when you created a logic app or a data factory job, the Azure policy automatically configured the diagnostic settings to send the logs to Log Analytics. And on top of that Log Analytics workspace, we were able to build an API. That API could query with the KQL, the Kusto query language, a very powerful language, could query directly on Log Analytics. And we were even able to create dashboards, workbooks, Azure workbooks directly on top of Log Analytics, even without the need for an API. So the API was an optional thing for customers who really wanted to design their own front ends, but for many customers, the Azure workbooks were already more than enough. So this is very important if you are expecting quite some loads. Think about not only your traditional data stores like SQL database, but have a look what's inside the box of Azure. For example, Log Analytics is very powerful. If you're thinking about IoT projects and these kind of things, definitely have a look at Azure Data Explorer, which is built on the same technology and which is a very scalable data store, which can help you to do interactive and batch queries on your IoT data. Same setup, same functionality, and also the same Kusto query language that you can use to query your Azure Data Explorer. My number 7 is actually a very simple project. It was just a kind of a lift and shift project, where we had an existing application that we needed to migrate to the clouds. Why did the customer want to migrate? Just because they want to also expose the functionality that they had to external partners. So the setup was a very traditional 3-tier setup. We had an Angular front end, a .NET Core API, web API, just a RESTful interface, and a SQL server underneath. And everything was running on one single Windows machine on premises. So we brought that to the clouds. We really wanted to bet on platform as a service technology because we wanted to avoid a costly management. So just we wanted to have everything as a service. So we went for static web apps, an Azure App Service where the API was hosted, and then a SQL database. The external partners, they were connecting to the static web app if people were connecting to it, let's say if people were logging into the customer portal, or they were connecting directly to the API if they wanted to have automatic integrations. Everything went very smooth. The integration was very nice and very fast. We did the migration in, I think, 1 week, and most of the work was just in setting up the Azure DevOps pipelines to do this deployment. The go live also went fine, but the more and more people were using the new platform, the more duplicate records that we identified. So that was a little bit strange, and after some investigation, it turned out that this was already an existing coding problem. It existed already, that problem, on premises, but only the problems started to become big when we deployed this on the cloud. And there were two reasons of it. First reason is the increased consumption, because now also external partners were using it, so the API was used more and more. And secondly is, of course, the distributed nature of the cloud. Not everything was running on a single virtual machine. We had network components in between. Some services might fail for a few seconds, so you need to make sure that your code is idempotent. And that was not the case. So idempotence is very important if you are doing cloud developments. And a function is actually idempotent if you execute it once, twice, or multiple times, that the result is always the same. In our case, the result was not the same because duplicate records were created if a certain message or an API call was processed twice. So you can easily explain that idempotence by having a look at a few examples. In this case, I have a client that is calling the server API. It's doing a request. The server is processing it in its eternal database and is returning the response. Everything is fine, everything is green. Second scenario is also good. The client is doing the request, the service is unable to process it, and it's returning an exception to the client. So the client sees the exception and everything is still going fine. The next scenario is not that good, because here we have the client that is calling the service. The API is processing the message or the request fine, but then when it wants to return the message, the response wants to be returned, then suddenly the network connection drops. So the customer, the client, is actually receiving a timeout and it's retrying again. But then your server side, your API, must be idempotent. And in our case, it was not like that. The same issue you have when you are consuming from a service bus queue or any other queuing mechanism. It might be that you send the message to the server is processing it fine, but then you fail to delete the message from the queue, so the message will be reprocessed again. So if you are doing cloud development, you have to deal with the distributed nature of the cloud, which means that you have transient failures, and your code needs to be able to deal with those failures. So how could you make this solution idempotent? One of the options is to introduce a client-side request ID. You can just keep track of the request IDs that you already processed. So if you receive a request that you already processed before, you can just return an HTTP 200 and everything is fine. Another option is to keep a server-side list of hashed requests. So if you keep the hashes of all the requests that you already processed, you can do something similar. You can also set on your database, on your system, a unique constraint on a combination of columns, a kind of a functional combination of columns that always should be unique. And if you have a unique strain violation, that you just gracefully capture that exception and you return an HTTP 200, because that means that this request was already processed before. And you could implement any kind of upsert functionality where it doesn't matter whether you do the create or an update, just make sure that you implement it the right way and that you think about timing, that you don't update a value with older values, so there a version or a timestamp is very important if you implement upserts. So integrations might seem simple at first glance, but make sure that you think about that idempotence messages should be able to process more than once. My next issue that I encountered was about scalability. We had a customer that had a very market-sensitive business, so there was quite some fluctuation in the demands that they had. For example, the summertime was very popular, in winter there was a decreased demand. There were no excessive peaks, but we needed to scale quite good. Not fast, but we needed to scale to big amounts. So if you look at scaling, there are actually two options. And the first option is to do vertical scaling. So just make your compute, your machine, your VM bigger. So more CPU, more memory. So that's a very simple way of scaling, because you don't actually need to change anything to your code base, but it's limited to the maximum VM sizes that you have at your disposal. If you really want to scale bananas, then you need to go for horizontal scaling, the scale out and the scale in functionality. So instead of making your machine bigger, let's just add some more machines. This is actually what Kubernetes is doing under the hood. It makes sure that your application can run on 1, 2, or maybe 500 VMs. It should not matter. But of course, you need to make sure that your code is able to deal with that multi-instance development. So for this customer, again, I used App Service, Azure App Service, a very nice service. And if you look at the scale up settings, you can choose different tiers. And what I did, I've chosen the smallest tier, so the S1 tier, which has the most limited memory and CPU capacity, because I wanted to also do auto-scaling. So my thinking was, okay, let's scale with the largest compute, so we are cost effective. So in Azure App Service, you can configure some rules where you say, okay, if CPU or memory is for a certain amount of time above 70%, let's add an instance. If we go below 50%, for example, let's decrease again and let's remove one instance. And you can set some limitations on the maximum and the minimum number of instances that should be running. So you have quite some control on how your application scales. So what happened? This was the load that we had to process over time. And the scalability went pretty good. We went from 1 instance to 2 and 3 instances. But then after the scale out, we didn't scale in anymore. So we remained at the top number of instances. What was the problem? Because I was using the S1, it had a limited memory availability because I took the smallest instance. So actually, even when my API or my web application was not running, it was still consuming 55% of the memory. And remember that my rule that I configured was to scale in again at 50%. So the scale out worked perfectly, but no scale in, so a lot of money was spent. So the solution is actually, and that's actually part of DevOps, but it's an aspect of DevOps that is often forgotten, but you need to learn from the behavior of your application in production. Because those scaling rules, you need to configure them at development time, and actually there, you just do it with gut feeling and common sense, but you have actually no clue how your application will behave in production. So we did learn, we configured notifications in production after this mistake, and we found out even that scaling with an S2 instance was cheaper than scaling with an S1 instance, because it had more memory available and than running an S1 in idle time. And we could also use the webhooks. So in Azure App Service, if there's a scale out or scale in event, you can configure a webhook to be called. So that's one we used on one hand to send events to our teams. So we had a Teams channel where we could follow up, we are scaling out and scaling in. So we, apologies, could closely follow up what was happening under the hood. And we could also use those events to scale up and down our SQL database. Because of course, if you're processing, your API power is scaling, you need to make sure that your database can also continue to cope with the increasing demand. So that was a very nice solution, but of course we were only able to do that by monitoring and learning from our application in production. The next issue is not about a mailbox, but about the outbox pattern. So we had a customer who had a very good scenario for an event-driven architecture, because they wanted to be more competitive in the ever-changing market. So they were convinced, and it was a good idea for them to apply an event-driven mindset. But then they had a microservice. This is just an example, but let's say a customer microservice. And when a new customer was created, they had actually to do two things. They needed to first update their database, so the state was up to date, but then they needed to send an event also to the event hub in our case. So the event could be spread across the company and other applications could subscribe on that. But what was the problem? They first updated the database and then we did send an event to our event bus. But what if that second step failed? Then our application was still up to date, but the other applications were not. So this was not a good pattern. To solve this solution, you can actually use the outbox pattern. And within the outbox pattern, you create actually a transaction over your database. And in that transaction, you will create your customer, but you will create also an entry in your outbox pattern that says, hey, you still need to send out an event for this customer that was created. So you do that in one transaction, so you are 100% sure that both operations will succeed or both operations will fail. And then you need to have an asynchronous process that is maybe polling on your database table, or that's maybe using change data capture to get notified when a change happened in that outbox table. And then you need to send that event that is in the outbox table to your event hub. And when you've done that, you can remove the entry or mark it as completed. And in that way, you have a reliable way of updating your own database and making sure that in the same transaction, you also trigger the process of notifying the other applications. So that outbox pattern is very good, and it's actually available out of the box in Azure. For example, if you're using Cosmos DB, you have the Cosmos DB change feed that is offering this. There's also a SQL binding for that, so you can very rapidly get notified when a change in a certain table occurs. You can also use it to do historical analysis, and you can rewind the tape so you can go back with the SDK in time and capture all the events that you want. And since recently also SQL database supports change data capture, it's actually a feature that is already existing for years and years in SQL, but it was not available in Azure SQL database. I think since this summer it is available, and you have now also an Azure binding, an input binding that is available that can trigger you when a change happened in a SQL database. Under the hood, that binding is using CDC, the change data capture functionality. And this makes us to the last but not least mistake that I made. This one was for an airline company that was working in the cargo, and they were heavily betting on low code. So they chosen the Mendix platform to go for low code, but they asked us to build a reliable API backbone on Azure. So that was, of course, very nice. So their Mendix was connecting to Azure API Management, and under the hood we had a multitude of APIs that were connecting to SQL databases and other database stores. So it was a quite complex but nice environment with a lot of cloud-native APIs. But the problem, Azure West Europe was down for a few hours, and all the planes could not leave because the required documents could not be fulfilled because Azure was down. So we had a look, of course, afterwards, how could we solve that problem? And actually, it was my mistake, because actually every time you start a new project, you need to think about SLA, high availability, and disaster recovery. So if you looked at the API backbone SLA, we were using 4 services, which all individually have an SLA of 99.99 or 95%. Of course, those services work together and are creating one solution together. So if you calculate the composite API, we actually end up with a 99.88 SLA. Of course, this is a very theoretical exercise, but at least from the theory, it learns that you could have 10 hours downtime per year. And actually, that was what happened with that customer. We had 4 hours of downtime in one morning there. So how could you solve this? It's, of course, always a technical, theoretical solution, but there are actually 2 ways to solve it. First is you can go geo-redundant. One region, Azure region, for example, West Europe, exists mostly of 3 data centers that are very close to each other. So if you go for the zone redundant setup, you can make sure that within every data center you have at least 1 instance running. That's very simple. You just need to check the box and pay for it, and then you are already protected against a single data center failure. If you want to be protected against a failure on a region level, then you need to go multi-region. Of course, multi-region setup is a lot more complex, because then you need to take that into account in your deployment process, and you need to have some kind of load balancing in front of it. So only do that if you really need it. If you deploy your solution across multiple regions, you have a new composite SLA to calculate, and it can be much higher. In this theoretical example, you could have 1 minute downtime per year. Of course, remember, this is always a theoretical exercise, because the way the SLAs are calculated for the Azure services is different for every single service. But at least it gives you a good idea of what to expect. There are quite some reference architectures available on Azure Architecture Center that can help you with this. So remember, high availability and disaster recovery. Always discuss this internally or with your customer and make a profound decision. But it's a balance between availability on one hand and cost and complexity on the other hand. And sometimes, an outage, sometimes you cannot solve it with technology. Sometimes it's simpler to maybe solve it through operations. I know quite some businesses if their environment is down, that they can run maybe 1, 2, 3, 4 hours on paper and then continue again in the digital world. Sometimes these solutions are much simpler, much cheaper than going for the full Monty on your technology level. So it's possible, it's more complex, but it's your choice to make. So as a conclusion, I think there are 2 main conclusions that I want to give you. The first one is invest in your Azure governance. The governance, it's about thinking about your resource consistency, separation of environments, cost management, security, release management, and business continuity. Very important to take that into account. I see many organizations that start with the cloud, but that forget this first step. If you want guidance on that, the Microsoft Cloud Adoption Framework for Azure is a very good starting point, and there are quite some partners out there that can help you with this. So this is to set the foundation for your Azure environment. If you're then more on the developer or architecture side, it's also good to have a look at the well-architected framework. Make sure that your design is taking benefits of the cloud and it's ready to cope with the distributed nature of the cloud. So there, the Azure well-architected framework is very nice, and there are specific areas that focus on some domains like APIs, like messaging, and there's also a specific domain on IoT. So go over there are quite some good examples and advice over there, so very nice. And in the end, we're all working with people, treat each other with respect, very important, because some people might already be further in their cloud journey than others, but just make sure, embrace everybody and make sure that they can learn together with you to find the right solution from a security, cost, whatever perspective. So thanks a lot. If there are any questions, you can reach out through the chats. And for the rest, have a nice day and enjoy the events. Bye-bye.